addition to magnification, resolution is also an important characteristic of our microscopes. Resolution is defined as the ability to identify two separate objects as actually being separate from one another. And on the left here, you can see an image, and it's pretty blurry. You can see the greens and the reds, but you can't see much detail. But here on the right, you're seeing a little bit more detail. And that's because this has higher resolution. Resolution is altered by several things. Wavelength is the first thing that we're going to talk about. Now, visible light has a long wavelength. Electrons in an electron microscope have a shorter wavelength, and shorter is actually better here. So the shorter the wavelength, the better the resolution. So an electron microscope is a better resolving of the image than a light microscope. Now, resolution is also determined by the numerical aperture of your lens. So let's get some examples. So our 4 times lens in our lab might have a numerical aperture of 0.1. On the other hand, a 100 times lens might have a numerical aperture of 1.25. Now, this is a mathematically derived number that you don't need to worry about, but what it does tell us is 1.25 is a higher number and will give us much more detail. So a numerical aperture that's higher, the number is higher, gives us a better resolving power for our lens on our microscope. Now, the maximum that we can get on a light microscope is around 200 nanometers, which sounds a lot, but an electron microscope will go to 0.2 nanometers. I should write that one out, 0.2 nanometers. So that's an electron microscope. And we do now have some other microscopes that will go even further. So 0.39 angstroms. I'm not going to talk about those kind of microscopes. They're very expensive, but 200 to 0.2 nanometers, those you should know that this is a higher resolving microscope. It's a much better microscope for seeing more detail. Refraction is also a concern for microbiologists. This is refraction. The easiest way to describe it is if you put your hand in a bathtub of water and it looks like your hand isn't connected to your arm, that's because the light is refracted from the water to the air. Similar thing happens with our microscopes. So if we look at a light source, we track this light, it comes up here through the lenses, through the condenser lenses, through the glass slide. Then we're going to say it goes through your specimen, but then it hits air. Then it goes back to glass and then up into the glass of your oculars. Every single medium here has a different density, or what we call a different refractive index. So you're going to be looking at refractive indices or refractive index. Now the glass slide right here has a particular refractive index. This is different to air. Air has a different refractive index. And then as it passes back to the glass here in the objective lens, that has another refractive index that's different. So we're seeing multiple different changes in refractive indexes. So it's going through essentially glass refractive index, then air refractive index, then back to glass refractive index. And as it does so, the light here is going to bend. And as it bends through these different refractive indexes, we will lose the resolution of the sample. Resolution, remember, is the ability for our lens to gather light and determine fine detail, i.e. 2 separate objects or more, as being independent of each other. Now, thankfully, oil, particularly the immersion oil that we use with our microscopes, has a refractive index that's similar to glass. So this is pretty much the same refractive index as glass. So instead of going glass, 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 air, glass, we are now going glass, 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 glass. So that means that we don't lose any of the light entering the sample. It will be captured by the lens, and we will be able to see the resolution that we need to identify and look at our samples.